Hi class. Today a lot of people were asking me about how to do the charges on that sheet that I gave you, and I just wanted to give that a little bit of clarification. So one way to generate the various species is to just take a group off. So for example, if I have a hydrogen and it's hooked to, say, a carbon, and that carbon's hooked to 3 hydrogens, all right? The way I would try to work out the charges on a hydrogen is I'd have to take that whole group off. And what I suggest is take the whole group off and leave the electrons behind. So what you want to think about is a hydrogen first that has 2 electrons. And you can do this with every atom, okay? This species has a negative charge. Why is that true? Because this has this has a valence number of 1, right, minus 2 electrons, so it has a negative 1 charge. All right, so this has a negative 1 charge. This is called a hydride, and hydrides actually do exist, or hydride-like species do exist. Now, how would I get to the radical? I would take 1 electron away from that. So again, what I'm considering is the hydrogen and a pair of electrons. It would be not unlike taking hydrogen gas and just taking one of the hydrogens off and then leaving the 2 electrons behind. So if I take it down 1 electron, what I have is a radical. Then if I take 1 more electron away, I have a positive charge. I have a proton. Okay, and that's what you would have called a proton in general chemistry. Now we could do this with every single one of those elements. Some of these are not on my answer key, and the reason they're not on my answer key is because you're not going to see them in the course. You probably will not see this in the course. Protons really don't exist. Protons are usually hooked on to whatever solvent that you're working with. But let's look at a couple others. So say I had a nitrogen. One way to do a nitrogen would be the same way. If I have a nitrogen, and let's say, again, it's hooked to a carbon group. So I'm going to make this carbon group an ethyl group. And one thing I have to say, some of you are getting way ahead of yourself. I mean that in the most complimentary way. But some of you are weeks and weeks down the road in terms of the work. And you have to give it a little time. Like, give me a little time to get through some things in class. Because we really have only had about an hour of lecture. So it's going to take a little while before you understand everything. It just takes a little while, okay? But right now, what you should be doing is maybe like translating structures. So for example, I'm getting a little off track here. If I wanted to draw this in bond line notation, that's how it would be drawn in bond line notation. So you could take any structure in your sheets and translate it back and forth a couple times and make sure you understand what's going on in that regard. You should also be able to take any atom in a molecule and calculate its charge. That should not be an incredibly difficult thing for you to do, and it would not be unreasonable for me to ask you that on the quiz, all right? It would be hard for you to generate these species that I'm going to generate right now, okay? So realize what you're going to be asked on Friday is pretty fundamental. But anyway, get in the habit of drawing your lone pairs in. One thing you should know is the valence of every atom. Okay, so say I had this structure. How would I get to an anion? All right. The way I get to an anion from this is I take an atom off and leave the electrons behind. Okay? If I leave those 2 electrons behind, so I've just taken the proton off, I want to leave the carbon part of it because I want it to be organic. So I'm making it organic. How would I do the calculation on this? This has a valence number of 5, or number of valence electrons is 5, minus 2 sigma bonds minus 4. This gives it a value of minus 1. So I'm purposely generating negative 1 charged species to begin with. So this is negative 1. All right, again, once you get the negative 1 species, how do you get to the radical? The way you get to the radical is you would remove, I'm going to draw this a little differently, you would remove 1 electron from that. Now I'm going to draw this in condensed formula. This is how you draw the condensed formula of that. Okay? This is a radical. This has a 0 charge. And then if I wanted to get to a cation, I would take 1 more electron out of this, and I would draw this. Now this is kind of a weird cation. Now I'm drawing it in bond line, okay? This cation is not on my answer key. The reason it's not on my answer key is it's very hard to generate that. Okay? So there are other ways you can generate cations. Another way to generate a cation from this kind of species would be if I added another proton onto it. In other words, here's the same structure again. In other words, if I throw a proton or a carbon onto that, I would get this. This is a different kind of cation. This is a nitrogen cation. This is also a nitrogen cation. This is going to have a +1 charge. Why? Because it's 5 minus 4, no lone pairs. So that equals +1 charge. Okay? What's different about them? This nitrogen is actually missing a pair of electrons. It only has 6 electrons around the nitrogen, so this actually has sort of like a void, an absence of electron density, whereas this is just sharing too much. So what's going on here is this pair of electrons now belongs to the N and the H, so the nitrogen only owns one of the electrons in terms of the bookkeeping. Okay? Now, in this case, this is truly a void. So if I added, say, hydroxide to this, I'm just making this up, but if I added hydroxide, I'm drawing kind of a bizarre situation. This negative charge would jump right in on that nitrogen and grab it, because that nitrogen is truly positive, okay? But in this case, this plus charge is a bookkeeping charge, and really the charge is on the surrounding atoms. So if I added base to this, this is just something to think about. The base would pull the hydrogen off that ion. Now, why would it do that? Think about this. This is not really a deficient nitrogen. It has 8 electrons around it. And remember, the dipole moment is really what dictates what's going on. So that nitrogen actually has a lot of electron density around it. Okay? Now, similarly, you could do a similar thing with oxygen. And I'm just running through this because some of these are written on the sheet and some are not, and it's because some are common and some are not common. So, for example, supposing I had this kind of compound. And I just thought I'd go over this a little bit because there were a lot of questions about this today, kind of understandably. All right, so this, all right, how would I get to the anion? An easy way to get to the anion would be just to take this hydrogen off. Okay, if I just take the hydrogen off, I'll leave that. If I just take the hydrogen off, this is what the structure would look like. You guys should get in the habit of drawing your lone pairs in. Lone pairs are not required, but I find when students don't write them, they tend to forget that they're there. Okay? So if I take that H off, this is 6 minus 1 minus 6. So once again, I've made a -1 charge state. That's what a -1 oxygen is like. Notice, I'm only working in the -1 to +1 range. I'm not going outside that range. I'm showing you different ways to make the charge. So, how can I make a radical from that? I may not even have the radical in the answer key because you guys don't really deal with oxygen radicals in this course. But the way I make the radical, and I'm going to draw a bond line, so there's a bond line notation of it. The way I make a radical is I take 1 electron away from that, and that's now 0. All right, so how would I make the cation? Take 1 more electron away. And honestly, I never did it this way until today because I was helping people to do this problem. And you guys deserve big credit because I give this worksheet every year, and it's very rare that anyone asks me a question about it, so it's kind of interesting. I think you guys are really doing it, so that's great. So this has a plus charge Y. This is 6 minus 1 minus 4, so this is a +1 charge. If you get so what I want to say to you is I do not expect you to be able to generate these, but I do expect you to be able to calculate the charge on an atom. When do you calculate a charge? When do you get a charge? It's when the atom doesn't have the correct number of bonds, okay? All right, so this is not the only way to have a plus charge. Think about this, right? This is your old friend, the hydronium ion. My last problem was modeled on your old friend, the ammonium ion, which you study in general chemistry. This has a plus charge. You've seen these before. This is nothing new. So what would be the other way to get a more realistic plus charge on that O? The way to do that would be to pop a proton onto one of those onto this oxygen. So I'm just showing you another way to get this, or it could be another atom. It doesn't have to be H. That should be an H. It looks like an I the way I drew it. Okay. So this, okay, again, using bond line notation, this has a +1 charge. This is a different kind of +1. This is a +1 where the atom is actually missing a pair of electrons, and it's very hard to make that because oxygen's electronegative. However, this is more commonly the way you see a positive charge with oxygen. The way you see it is with 3 bonds on the oxygen. The oxygen is sharing too much, right? Normally, it owns that pair of electrons, but it's sharing it. So in terms of bookkeeping, it's lost an electron to that H. But again, what's going to happen chemically? Chemically, if I added a base to this, the base would pull this H off. It's not going to attack the O because the O is not deficient. This O is deficient, and it's kind of an unrealistic O in a lot of ways. Okay, so that's just to help you with that sheet so you understand it a little better. In terms of the quiz, again, you shouldn't be getting too worked up about this quiz. This quiz will probably be the easiest quiz you have all year. What you should be able to do is translate structures. So what I mean by that is, if you were given some structure, say for example, this, I'm just drawing something like that. You should be able to take that structure and redraw it in a Lewis dash formation. In other words, you should be able to do this. And this takes a little practice, and to be honest with you, so, how do you practice? Well, there aren't a lot of formal problems in the textbook to do this. However, every structure can be translated. You don't need formal problems to do this. So all you have to do is look through your packet, and every time you see a structure, think about what the structure would be in Lewis dash. I'm just doing this. This is not the neatest job I've ever done here. Okay, here we go. You can put your lone pairs in if you want. That's good practice. You want this to become second nature for you. It's one thing to kind of get it. It's another thing to do it rapidly, all right? So you should be able to take a structure like that and fill in all the carbons and all the hydrogens. Some people do it right on the structure like this. And then they say, oh, this has 2 bonds, so the other 2 bonds must be hydrogens, okay? Any structure, anywhere in your notes, anywhere in your packet, you can do this translation. If it's drawn like this, you can bring it back to that. At this point, don't get too overly concerned with condensed formula. We'll work on that a little bit later. Okay, thank you.